Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, as we discussed in the last lecture that we have concluded the chapter dealing with the bending stress. Now, we will be taking couple of numerical problems. So, the first problem is that if you look at this problem, okay, a steel beam whose cross section is shown, I mean I will be showing the figure right now, carries a uniform load per unit length including weight of the beam of course of 29 kilonewton per meter. Calculate the maximum bending stress in the beam. So, that is the problem. Okay. Let me draw the figure. So, this is the cross section of the beam I beam. This is 210 millimeter. This thickness is 25 millimeter, this thickness is 12 millimeter, this is the centroid of the I beam, okay, that is your Z axis, and this is 175 millimeter, this is 175 millimeter symmetrical cross section, this is also 25 millimeter. Okay. And the problem says this is the beam, simply supported beam. Simply supported beam. You have uniformly distributed load of 29 kilonewton per meter as given in the problem. The length or the span of the beam is 7.5 meter. Okay. So, this is the problem. So, you need to find out the maximum bending stress in the beam. Now, if you want to find out the maximum bending stress, if you recall the equation of bending stress is this. Right. Now, if you try to find out the maximum, if this is going to the maximum, then this has to be maximum, that means the bending moment has to be maximum, as well as y has to be maximum. What is y? That is the distance from the neutral surface to the upper fiber or the lower fiber, right. So, this distance should be maximum. Now, IZZ is constant if you are not dealing with the different cross section or the variable cross section along the span. So, IZZ is constant for any particular cross section, is not it. For this I beam, basically you can calculate IZZ and that is constant. So, you need to maximize both the things together to get the maximum bending stress. So, what I need to find out? I need to find out the maximum bending moment in the beam under this kind of loading condition and the fiber at which the maximum or the maximum or the extreme fiber rather from the neutral surface. Okay. So, obviously, the neutral surface is this which you will be passing through the centroid of the cross section. So, the extreme fiber will be always either this side or this side, right, top or bottom, depending on that you will be getting tension or compression, that is different thing. we are talking about the absolute maximum bending stress, whether it is compression or whether it is tension, that is not the matter of concern. We are going to find out the absolute maximum bending stress. So, y has to be maximum. So, as I told you that it should be either the extreme top surface or the extreme bottom surface, then y will be maximum, that is okay. Now, let us find out the maximum bending moment first. So, the maximum bending moment, as you know from our earlier discussion, for this kind of simply supported beam with uniformly distributed load, the maximum bending moment will be happening at the center, right, and that maximum bending moment, that you can check it. I mean, I am not going to do that thing again, because you are quite familiar to the solution procedure, and by which you can find out the maximum bending moment. So, maximum bending moment for this kind of loading system or the beam will be W L square by 8, that you can check it, where W is nothing but the uniformly distributed load 29 kilonewton per meter. So, I can simply write 29, and L is the span of the beam, that is 7.5 square by 8, okay. That comes as 102 kilonewton meter. So, that is the maximum bending moment, okay. So, you have got the maximum value of this bending moment. Of course, maximum value of y is also known to you, that is either 175 top or bottom, no matter, okay. Now, you need to find out IZZ for this I beam, okay, and I hope that you know how to find out IZZ for this kind of cross section, okay. So, let us find out that. So, IZZ will be equal to 12 into 300 by 12, okay. 12 into 300, 300 is 175 plus 175. So, that is the total length, okay, that is the total height, okay, into 12 divided by 12. So, this is the way you can find out. I mean, there are several options by which you can find out that IZZ. You can find out the IZZ for the whole say cross section, like considering this is a rectangular beam, rectangular cross section, and then you just subtract this part. There are several ways, as you know. So, that I am not going to repeat. So, I am just calculating that thing plus 2 times 210 into 25 cube by 12 plus, this is the parallel axis theorem, okay. We are incorporating the parallel axis theorem, (162.5 square). Agreed? So, this is the IZZ considering this flange, okay, with respect to its own CG. Now, this CG has to be shifted because this is the global CG for this cross section. So, we can use the parallel axis theorem like this, okay, fine. So, this will be coming as 3.048 into 10 to the power 8 millimeter to the power 4, which will be nothing but 3.048 into 10 to the power minus 4 meter 4, okay. Therefore, you can find out sigma x, which is equal to minus, if this has to be maximum, this is also maximum, y max divided by I z z, okay. So, that comes as, so MB is given. So, just we are putting the values, MB is equal to 102 into 0.175 in meter, okay, by 3.048 into 10 to the power minus 4. So, we are not considering this sign because this, I mean, if you consider the tension, okay, that bottom fiber that will be under tension. So, we are putting y max equal to negative, so negative will be positive. Okay. So, that gives me 58.6 into 10 to the power 3 kilonewton per meter square. Okay. Understood? So, this is the way you have to calculate the bending stress. Now, coming to the next problem. The next problem says the sketch, I will be showing the sketch right now. The sketch shows the cross section of a T beam which is transmitting both a bending moment and shear force. What is the ratio of the maximum bending stress in the stem? Stem means wave, whatever we discussed earlier. Stem and wave both are same. In the stem to that in the flange. Okay. And what is the ratio of maximum average shear stress tau xy in the stem to the maximum average shear stress tau xz? Please remember, because tau xz is more critical for the flange, okay, in the flange. So, there are two things. One thing is that you have to find out the ratio of the bending stress in the stem as well as the flange, and you need to find out the ratio of the shear stress. Shear stress, of course, tau xy is critical for the stem and tau xz is critical for the flange. Already we have seen that. So, that ratio also has to be found out. Okay. Now, let's draw the cross section first. Okay. So, this is the T beam, very thin flange and very thick stem. Okay. This is Z axis, okay. Normal to the board is your x axis. Okay. So, this is given by a by 2, this is given by a by 2, this is given by 5 by 4 a, this is 4 T, and it is given in the problem T is very less than A, and this thickness of the flange is T. Okay. So, this is the problem. So, we need to find out the ratio of the stresses. Now, before going to the analysis, what we need to find out? We need to find out the neutral surface, right. Here actually if you look at the cross section with respect to z axis, it is not symmetrical, right. One side you have the flange, other side you do not have the flange. So, therefore, you can't say that the z axis or rather the neutral surface will be passing through the midpoint of the stem. You can't say that, because you need to calculate or need to find out the CG of the cross section, okay, by following the same procedure whatever you have learnt in physics or maybe some other advanced level of physics course. So, by following the idea or by following the principle, you can find out the CG of this cross section, and that CG, and through the CG basically your neutral surface will be passing. Okay. So, let us find out the CG. Say that is nothing but say y bar we are saying. So, this is say that is my say y bar. Okay. So, that will define the CG distance. Okay. So, this y bar can be obtained as you know, I mean I am expecting and I am anticipating that you know how to calculate the CG of a particular cross section. Okay. So, 5 a by 4, okay, AT into 5 a by 4 plus 4T into 5 a by 4 into 5 a by 8, okay, divided by the area and since this is true because t is very less than a. Okay. So, based on that we can write this equation for y bar, and that y bar will be coming as 0.73 a. Okay. So, that means first job is done. So, you have identified the location of your neutral surface. Okay. So, once you have identified the location of the neutral surface, then your stem sigma x max is equal to m I z z y max stem okay. So, that is nothing but m. I am not considering the sign. Okay. So, that is quite understood. Okay. So, m divided by I z z, because m is constant for this cross section, to 0.73 a. That is the y max for the stem. This is the neutral surface. So, the extreme bottom surface is points y bar distance apart from the neutral surface, that is nothing but 0.73 a. So, that you have got. Now, in case of flange sigma x max, that is m I z z. Okay. Y max, we are taking the absolute value. Okay. We are not talking about, we are just interested in the value, because we are going to find out the ratio. We are not talking about the sign, whether it is compression or tension, that is immaterial for this, at least for this problem. Okay. Only the value will be the major constant, m I z z. Okay. So, that will be 5 by 4 a minus y bar. So, that will be coming as 0.52 a. Okay. So, therefore, your stem sigma x max, the ratio of that to flange sigma x max is equal to 0.73 a by 0.52 a, which is nothing but 1.4. So, this is the first job we have done. Now, the second job is to find out the ratio of the shear stress. So, maximum tau xy occurs at y is equal to 0 in the stem. That means at the neutral surface. Here for the stem at least tau xy will be maximum here. Consider the parabolic distribution, do you remember that? So, that will be maximum at the neutral surface. So, at y equal to 0 your neutral surface is passing through that point. Okay. So, your q, that is the first moment of area, understood, the first moment of area with respect to the neutral axis. Okay. So, that will be given by 4t into 0.73 a, that is the area, this area, because when you are talking about the stem, so this whole area will be coming into the picture, and the first moment of moment arm is 0.73 a by 2. So, that is coming as 1.06 a square t. Okay. Now, for flange tau zx is max at the, as we have seen when we were discussing about the development of tau zx, at the junction between flange and stem, right. That means it will be here, okay. It will be here, somewhere here, okay. This will be maximum. So, Q for half flange is equal to, that is the first moment of area, which is nothing but we are considering, because this we are considering the whole part. So, we are considering here it is maximum, okay. So, A by 2 into T, that is the area, okay, and that area, that moment of this area with respect to z axis, that distance is 0.52a from the z axis. So, this is the area, okay. When we are talking about the flange, this is the area we are considering, and the moment term is this, that is nothing but 0.52a. So, that gives me 0.26 a square t. Thus, stem tau xy max by flange tau zx max is equal to V by Izz. V is constant, Izz is constant, 1.06 a square t by 4 t, Vq by Ib. Ib means thickness is 4 t, okay. If you look at this figure, thickness is 4 t in the stem, okay, divided by Izz for the flange, Izz by V. For the flange, the thickness is t, okay. If you look at the thickness of the flange, that is t. So, for the wave it is 4 t, for the flange it is t. So, t by 0.26 a square t, okay. So, from this I can get, this is 1.02. Understood? Now, you have got the idea that how we can calculate tau xy, tau xz in the flange as well as in the stem, and then we can, how we can find out the bending stress and all those things, you are familiar to that, okay. Depending on the cases, depending on the situation, you can calculate, or few things you need to know: how to find out the centroid of a particular cross section, because neutral surface will pass through that, how to find out the Izz, that is moment of inertia, okay, for that particular cross section with respect to the neutral surface, and how to find out tau xj, tau zx if it is T beam or I beam. If it is a rectangular beam or the square beam, then basically there is no problem, only tau xy will be participating, or tau xy will be contributing there, okay. So, with this I will stop and I will conclude this chapter. So, in the next class we will see the deflection of beam due to bending, and there we will be discussing that whatever we have learned here, based on that this curvature relation and all those things will be coming in the picture, and based on that we will be defining the, or we will be deriving the expression for the deflection. Thank you very much.